Thank you for tuning into this week's episode of the Rising Laterally podcast. This is Arjun Sachdev.
And this is Jay Ballou. We hope you find something here that offers you new meaning or a fresh perspective.
If you do, we encourage you to give it life.
Be bold.
Experiment.
And most importantly, bring it into the interactions with the people you surround yourself with.
And see what happens. Today we have the incredible opportunity of being able to sit down with Lawrence Krauss to talk about his new book, The Physics of Climate Change. He is an internationally known theoretical physicist and the author of hundreds of articles and more than 10 books, including New York Times bestsellers, The Physics of Star Trek, and A Universe from Nothing. He received his PhD from M.I.T. and then moved to the Harvard Society of Fellows. After 8 years as a professor at Yale, he was given tenure when he was still in his 30s. He's also taught at Arizona State University and Case Western. This man has made significant contributions to our understanding of the origin and evolution of the universe, and is currently president of the Origins Project Foundation and host of the Origins podcast with Lawrence Krauss. It's an absolute pleasure to have you on with us. Thank you, and welcome to the show.
Oh, well, it's a pleasure to be here with you virtually.
Yeah.
Excellent.
Yeah. 3 voices in one consciousness. That's what we like to say.
Yeah, that's right.
And look, let's just get right into it because there were so many mind-boggling stats and moments throughout your book. So I want to get into the conversation with where you started your book, which was around the Mekong River. So after reading the book, I realized that this is a microcosm of what's happening with climate science and its immediate impact on humans. So what's happening there is not good. So let's start with the Mekong River.
Yeah, well, it's not just not good, but it's kind of a perfect storm. The climate change is good. Well, in some places, depending on what we do, it may not be gradual, but on the whole, it's a gradual change, kind of like the famous proverbial frog in water that gets heated up. And
Yep.
But some places are much more sensitive due to a confluence of circumstances, and the Mekong Delta is such a place. First of all, the other thing that's important about it, and one of the reasons I started the book there and ended the book there, is not just because of the impact on me, but we often think of climate change is going to affect all these people out there, and it becomes kind of a general bunch of statistics, and it doesn't, and the human impact, it's hard to bring home. And I think human impact matters. And so I wanted to talk about a specific place. And in this case, it was the Mekong River, not just abstractly, but because I'd spent time there a little over a year ago, going up and down the river with leading a group of people, and in researching the situation, began to realize how sensitive it was, because that river is remarkable. It's one of the bigger rivers in the world, but it has more freshwater fish than almost any river in the world. More fish are caught there than all of the fish in all the lakes and rivers in the United States. But more importantly, it floods and it causes this incredible rice plain, if you wish, flooded plain, that is perhaps the most fertile rice growing region in the world, supporting between 40 and 60 million people.
Wow.
And it's incredibly flat. And as I talk about at the end of the book, we now realize, although it's just new, that almost 90% of South Vietnam is less than 1 meter above sea level.
Wow.
And this river holds back the South China Sea, which happens to have a big tide, it turns out, one a day, which is kind of unique, as I talk about, but not really unique, but unusual. And the fact that the river can hold back the tide is incredibly important, because if it didn't, then that freshwater region would become brackish and you'd have mangrove swamps instead of rice. And so you've got the fact, not just the fact that if sea level rises, as it's inevitably going to do by at least a half a meter this century, you've got the fact that, so it's not just the loss of land, if you wish, it's the fact, the loss of livelihood, that river itself, supports all this people. So, and the thing is that made it more poignant, I think, for me, is that that area is home to these remarkable cultures of people. And if you go there, these are regions that have suffered before you were born incredible hardships due to wars, genocide, and yet the people are just so vibrant and happy and not bitter, and to think that they may be facing something that's much more severe in the long term than any of those things in terms of the health and livelihood of that population, and it's not of their own doing. That it's largely due to the impact of what was really the first world over the last while, because carbon, as I described, that we put in remains there. And so that makes it more poignant for me as well. And anyway, it's an interesting situation, not just because it was personal and not just because of the perfect storm of climate change, but also because some of the realizations of how severe it is have just been in the last year or two. And I found that amazing that the different independent studies suddenly changed our picture. You'd think we'd know sea level elevation or elevation of land in the 21st century. You'd think we'd know it pretty well. And it's in fact that we didn't. And it's just remarkable to me. And it's not just South Vietnam. It turns out one of these studies used a neural net to actually renormalize. This is all done by space, by looking at space and projecting down and trying to determine distances. But those distances are good to a few meters, which is fantastic if you care about the elevation of large mountains and global elevations. But when a meter matters, then a small systematic error, which is well within the expectations of the experiment, can have a dramatic effect. And moving much of the world down by a meter, which is what the new projections show, puts another in anywhere up to 90 to 250 million people potentially below sea level in 2100. We've gone way ahead of where you intended, but anyway.
No, that's incredible, because at the end of the day, all those people are not as resilient as the people in the Vietnam region. That's for sure. Number one.
Well,
Number two,
Bangladesh, and that's a point I want to make too. Which let me make it early, and we'll probably need to later on. It's not all doom and gloom.
Mm-hmm.
We realize the point of this is, as I think I said in the book, the future is heading towards us like a freight train, but it's on tracks that we built. And so we can in principle do something about it, not necessarily stop sea level change, but we can know what's happening, and fortune favors the prepared mind. And we should think about what's in the interest of the first world. And it's really, this thinking is really hard for a lot of people in a lot of countries. First of all, thinking globally is certainly unknown for the most part in human history.
Yeah.
And we need to. And it's really going to be a hard slog, and I'm not necessarily optimistic. But we can actually think from a not an altruistic level, but a self-interest level. Is it worthwhile spending money to help? The sad part about climate change, because it sort of interacts differentially around the world. The places that'll be hit first are near the equator, which happen, for better or worse, to include a lot of poor countries, right? And also countries that didn't contribute to the problem in the first place.
Yeah.
So as I say in the book, when I was a kid, my parents had a little store and that I worked in, and there was little trinkets, and there was a little sign up there that said, "If you break it, it's yours." And you kind of think about that with the world, so you may think we have a moral or ethical imperative, but maybe morals and ethics don't matter when it comes to global foreign policy. In fact, I generally think they don't. But what happens is self-interest, and you've got to say, well, is it in our self-interest to perhaps assist in building the infrastructure, which we can do, and to moderate and ameliorate those problems, and not just to help them, but ultimately to recognize that the problems that are going to result for the rest of the world will be less. Climate refugees less, socio-political problems less. And so there are good reasons to consider for the first world to take action in places other than in the first world.
Absolutely.
Again, I'm way beyond your questions, and the first questions already taking me.
All good. This is perfect, because at the end of the day, let's add some context. I mean, if you don't think this hits home for you, by the end of this century, almost every major coastal metropolitan area in the world will be partially submerged. So you're talking London, Tokyo, partially. Miami. Yeah,
well,
partially
it will
submerged.
be. Now, when you say will be, it's important, because I want to stress, as I said in the book, it's like Charles Dickens, The Ghost of Christmas Future. The future as it might be, okay?
Mm-hmm.
Cratchit, what was it? Bob Cratchit's family might be miserable, but Scrooge could do something.
Yeah,
and so,
that's true.
And so the sea level will rise, and the cities will be below. Some cities will be below sea level, but much of Holland is below sea level, and it's a pretty nice place to visit. And so you have to recognize that yes, these things are going to happen, but they'll only be submerged in some sense if we let them be submerged. Okay.
Right.
Maybe it would make sense then to get into the modeling at this point. I think before jumping in there, it would probably be helpful for the listeners to have a sort of potted summary of the carbon cycle. So you explain in the book how CO2 is released in the atmosphere. Much of it is reabsorbed by the oceans and ultimately cycled through the Earth's crust. I was actually not familiar with that process, so I was wondering if you could maybe just give us a quick summary of the carbon cycle so we understand the
Yeah,
dynamics here at play.
sure. I mean, I'm familiar with it because a book I wrote called Atom once, which was about an oxygen atom from the beginning of the universe to the end. And I learned about this cycle. There's a geological cycle. Look, life has transformed the Earth. But in the absence of life, there's a carbon cycle, which has really been incredibly important for moderating many aspects of the Earth, including its climate. When in the early Earth, there was no free oxygen. Oxygen was a poison for life. In fact, we're lucky there was no free oxygen because oxygen burns things and life is just controlled burning. And if free oxygen had been around, the organic materials would have been oxidized and there'd be no energy left for you and I to have this conversation. But what there was I think 10 or 100,000 times more carbon dioxide in the atmosphere than there is now, of vital importance because the sun was 15% less bright back then, and that meant the Earth would have been frozen solid, except there was a global greenhouse effect that kept the oceans liquid. But then there's kind of a self-moderating effect on carbon in the sense that when there's a large carbon in the atmosphere, it dissolves in water, forming carbonic acid, which then can interact with the rock, forming calcium carbonates, for example, and leach away the calcium carbonates, and that falls to the sea level, to the floor. I mean, to the sea floor, and then global plate tectonics cause some parts of the Earth to go down into the mantle, and so that stored carbon gets put down into the mantle, and that did reduce the carbon abundance a lot. But what eventually happens is when it reaches a certain level, that carbon once it gets hot enough, the carbon gets released as a gas and carbon dioxide and released by volcanoes. And so there's a cycle, and it takes about 100 million years for a given carbon or oxygen atom attached to CO2 to cycle through the Earth and come back up. And that natural cycle puts around 3/100ths of a gigaton. A gigaton is the sort of quantum of interest here. A gigaton is a billion tons of carbon. 3/100ths of a billion tons of carbon per year gets cycled through the Earth that way. The volcanoes, and it's just a ton of cycles. Volcanoes are emitting it. It's being subducted, and so that is the geological carbon cycle. But life changed everything, not just by producing oxygen in the atmosphere and also producing carbon dioxide in the process of photosynthesis, in the process of plant growth and through photosynthesis. Plants also respire, so they also release carbon dioxide, and it changed everything. And to get to the heart of it now, the reason a gigaton is the quantum is that humanity is releasing 10 gigatons of carbon into the atmosphere every year. Now, I remind you, the geological cycle involves 3/100ths of a gigaton.
Yeah.
Wow.
And for some people, I still see it happening in comments saying, how can humans, affect things and at a much bigger level? And in the book, one of the fun things for me in writing books like this is that I learn things, and I did not know. First of all, the science behind climate science is not new. It's not rocket science. It goes back in some ways 200 years almost. And this guy, Arvid Högberg, in Sweden in 1894, did a wonderful calculation. It's a great back-of-the-envelope calculation that I would love to do for an introductory physics class if I were teaching one again. He said, well, he estimated how much carbon was in the atmosphere, and you could do it roughly in 1894, but then about 300 parts per million. Okay. And said, well, let's say you take all that and you turn that carbon into, oil, into liquid or solid. Take all the carbon in the atmosphere, turn it into liquid. How thick a layer would it cover the Earth? It's 1 millimeter. And then he said, well, look, life persists throughout the Earth and the continents and the sea level more than 1 millimeter. So life clearly can impact on the carbon abundance in the atmosphere. Forget for burning of fossil fuels, but life, the very existence of life changes that. And
Mm.
he realized that early on. It's a wonderful calculation. Now, when we are using fossil fuels, we're not just using the top millimeter,
Yeah,
right?
yeah.
We're exploiting the history of life for over 50 million years before the dinosaurs, etc. And so we're extracting. It's not surprising that we are utilizing amounts of carbon and generating carbon in the atmosphere that's huge compared to natural processes. And the remarkable, or I guess it is remarkable, it's also in some sense terrifying thing, is it so that if you consider how much 300 parts per million in the atmosphere was of carbon, that's about 600 billion tons of carbon. Okay.
Okay.
600 billion tons existed in the atmosphere before. And every year we pump 10 billion tons in.
Right.
And the important thing is about half of that stays in the atmosphere. Okay. But the important thing is that it stays in the atmosphere. I coined this term, at least for my lectures. I don't think I did in the book, called the Las Vegas effect. Namely, what happens in the atmosphere stays in the atmosphere. And it's not true for individual carbon atoms. It's not. Individual carbon atoms get exchanged with the ocean. Carbon dioxide gets exchanged with the ocean on the order of a year, but it gets absorbed and then released. The net abundance of carbon, however, does not change it over a year or 10 years or 100 years. It takes the carbon we've dumped into the atmosphere that's there now will take almost 1,000 years, and in 1,000 years, it'll still be 50 or 60% of it still there. And that's the crux of the issue. The reason it's worth talking about now is that just think of things since, say, 2010. In 2010, when this issue was being argued just as strongly, okay, we were still emitting about almost 10, we've gone up, but almost 10 billion tons of carbon. In the last decade, therefore, we've put in 100 billion tons of carbon, at least 50 billion of which are remaining in the atmosphere. And so we've changed things already by an amount that, and that's going to stay there for 1,000 years. And so when you say, well, this is an issue, but we can deal with it later.
No.
The problem is it's a lot harder. It's a lot harder to deal with now than it would have been in 2010.
Yeah.
Because we have almost 100 billion tons more carbon that we dumped up there. And if you want to keep things at a level, and the book is about how simple and basic the calculations are about of radiative forcing and heating up. If you want to keep things to a level of a certain temperature rise, that says you can't add more than X amount of carbon dioxide. And every year that X, we get closer and closer to zero. And if we don't do anything by 2030, that window will be closed.
Right. It's shocking. It's mind-boggling. And so, I mean, if anyone's asking, hey, what happens if we stop emitting tomorrow, or what happens if emissions continue at this current rate, you now have your answer. It's already there. And
it's there, and there are a lot of things that are written in stone. Climate change isn't in the future. It's happened already, and there are things we've done that can't be easily changed. Sea level rise of 0.5 meter is more or less written in stone, not because of melting of glaciers, but another thing that I didn't know about before I started to think about this is that at least half of it's just due to the expansion of water. As it heats up, water expands. So over the last 25 years, almost 50% of that sea level rise we've experienced already is just water heating up. And so, and it's like, if we stop it now, well, there are predictions you can make of what can happen. If we business as usual in 2100, it's a whole different game. And we're talking, I guess the other thing that's surprising to think about is carbon in the atmosphere really started to be measured by Charles David Keeling in 1950, 1953 first, but 1958 seriously. It's been measured every day since then.
That's the Keeling curve, right?
Yeah, the Keeling curve in Mauna, in Hawaii, and in the Antarctic. And every day for over 63 years now, that's been measured, and you can see it. And to think, from the time he started measuring it, it was 315 parts per million when he measured in 1960-ish. Okay, now it's 420, almost 417. It's increased by 30% in the time I've been alive. And that's so, that's a significant increase in a fundamental quantity that describes the atmosphere of the Earth.
Absolutely.
In a human timescale. Once again, carbon is, people say, well, carbon varies and the temperature varies, but that's over geological timescales.
Right.
And moreover, over the last million years, carbon has never been anywhere near about what the highest it's ever achieved was 300 parts per million before the Industrial Revolution. And so for almost all of human history, the carbon level was around, 190 to 275 and there were many ice ages and lots of little things, but we are in a time that's different than any period in the last million years when it comes to carbon dioxide in the atmosphere. And the interesting thing is that it's simple, it's basic physics. It's not simple, but it's basic physics to understand how that ultimately leads to heating of the earth.
Sure. Absolutely. You said a lot there. And I mean, you mentioned Keeling. I think one of the fascinating factors about your book was some of the history in terms of the scientists that have had a major impact. So Keeling was obviously one of them in 1958. But two others, I think, that are interesting to learn about. One was John Tyndall and another was August Arrhenius. Can you tell us a little bit about them? Because apparently they're pretty important.
No, it's great. It was fun for me. And I think that's a fun part, I think, for people to, in my books, I like to try and put a little bit of history to put the face in science and how we, how do we learn this? And it's often, kicking and screaming. And Tyndall was an Irish scientist, basically the first person to try and study the absorption of infrared radiation. Earlier it was called dark radiation. I mean, people knew about it. They called it dark radiation. It was a guy, actually, the first guy was a guy named Fourier, who, if you've ever taken physics or math, you know about Fourier series. And Fourier was the first person to really say, hey, there's a problem here. Because again, a high school level physics problem you could do was to say, okay, we know how much energy is coming in from the sun. If the earth isn't heating up, it's got to radiate it all. And if it's radiating like a single black body, what should the temperature of the earth be so it can radiate the radiation coming from the sun? He did that back of the envelope calculation and found out it should be 18 degrees below 0 Celsius, or maybe 30 degrees below 0
Not what
Fahrenheit.
you'd expect necessarily.
And that's a problem, right? I mean, it's wonderful when you do such a problem because you find out, hey, there's something wrong here. There's something we're missing. And he was the first one to say, well, maybe the blanket of the atmosphere has an effect on stopping the earth from being 30 degrees below 0. And of course it does. And then the first person to really kind of put meat on that in the sense of the data of measuring how radiation is absorbed when it goes through carbon dioxide and other greenhouse gases was John Tyndall. But the person who kind of the father of modern greenhouse effect, which, as I talk about in the book, has nothing to do with greenhouse. Well, very little to do with greenhouses. It's poorly named. Poorly named was actually not August, but Svante Arrhenius. It's okay. I get it wrong half the time too. But a Swedish chemist, and his life is interesting to me because, I mean, I'd heard of him, but I didn't realize the issues, which were kind of interesting. He was obviously not a very likable character, and he had a hard time. But when he did his PhD thesis, basically he got what you would call a D nowadays, and then he petitioned to have it raised, and it was raised to a C.
Oh, great!
And then somehow he got on the faculty at the university against the voting of a lot of the faculty members, but he made it on the faculty at Uppsala, and then became what is effectively the president of the university again over some protests, right. and then got barely voted into the Royal Swedish Academy of Sciences around the time that the Nobel Prize was created. Okay, and then he became head of the
early 1900s, right?
Yeah, around 1900, 1902. And he became the head of that. And then it's kind of interesting that coincidentally he became the first Swede to win the Nobel Prize. And so you might think, okay, well, there's a lot of nepotism here. In fact, what he did was incredibly important chemistry. He deserved it as it worked out. But it is kind of interesting. But he in 1896 was the one who really wrote a paper and then began to speak out on how human industrial activity could increase carbon dioxide and change the climate of the earth in a way that he was so looking forward to, because he said, this is the best thing that can happen because I live in Sweden. And just think of what would be better if the earth was warmer. And of course, he didn't think of other issues. He actually
Right.
borrowed the work, and he borrowed, but he didn't steal. He actually translated the work of Arvid Hogborn, who'd really done a lot of the early estimates that were necessary, and translated it for other people to read. And then, he popularized it. And interestingly, there's another scientist that you didn't mention, a guy named Newt Angstrom, and the reason that name rings out to anyone who's studied any physics, because angstrom is a unit of length. The angstrom is relevant, basically the size of an atom, more or less. And I thought Newt Angstrom was the Angstrom that was named after. It was actually his father, but he actually pointed out all these reasons he thought Arrhenius was completely wrong. And and his reasons turned out to be all wrong. One was an experimental misinterpretation of experiment that I described. The other was a misunderstanding of how carbon dioxide absorbs versus water in the atmosphere and the nature of that. And he thought water and carbon dioxide absorb in the same region. So increasing, if water already absorbs absorbs infrared radiation, then carbon dioxide isn't going to change anything. And he didn't know that basically water in the relevant range of infrared radiation absorbs in sort of peaks and troughs, whereas carbon kind of absorbs uniformly, and all those troughs get absorbed, and little things like that. And so he basically, his arguments held back the kind of acceptance of Arrhenius's arguments for some time, and now we realize they were wrong. I mean, not Arrhenius, but Newt Angstrom.
Right.
And we understand two things. We ultimately understand, and I talk at great length in the book here, and we can go into it if you want, how carbon dioxide absorbing infrared radiation, ultimately, what it really does is one term. It really, this fundamental equation is not complicated. If the Earth temperature is uniform, then energy in equals energy out.
Yeah.
That's what Fourier calculated in 1824, but he didn't use the atmosphere.
Right.
So if the Earth isn't going to get hotter, then energy in equals energy out. We know the energy in. We know the sun's radiation. We know how much is reflected and how much is absorbed. And what happens ultimately is, it's the end result is sort of simple. The increase in carbon dioxide in the atmosphere causes the atmosphere to become a little more opaque to the radiation the Earth might radiate into space in the infrared. And what happens is that when you think about it, the radiation that gets into space is the radiation that comes from the top of the atmosphere. Because if it's radiated earlier, it gets absorbed. The only radiation to make it out into space is the top of the atmosphere. If the Earth becomes a little more opaque, then the top of the atmosphere where radiation is emitted is a little higher. You have to be a little more sparse. And higher up means colder. So that means the Earth is now radiating from a colder level. But the intensity of radiation of a hot body goes as the fourth power of temperature. So since the Earth is now radiating a mass from a higher elevation and a colder elevation, it's radiating less energy into space than it would have otherwise.
And keeping
and
more.
But it's keeping the same amount and radiating a little bit less.
I see.
Difference we call radiative forcing. It's not a huge amount. It's about 2 watts per meter squared, per square meter, 2 watts. But there are a lot of square meters. That extra 2 watts per square meter is not only theoretically what we would predict, but the important thing is we can actually measure it in some sense. We can measure, as I showed, there's actually measurements of radiation coming down versus going up. And you can see which radiation gets into space and what doesn't. And so you can then turn that into saying, well, and it's a little bit of physics to say, if there's that extra heat, how much will the temperature change? And globally, you can approximate it. Obviously, locally, it's much more complicated because there's air currents, there's differential rate. The sun's maybe right ahead and over the equator, but it's not. The rays aren't hitting the the northern hemisphere the same. So there's complications, but you can estimate on average what that temperature change will be, and the increase in carbon dioxide over the last of the 30% increase translates more or less into a 1% change in the amount of heat being emitted versus being absorbed. And that turns out to be in that 1% is more or less 1% temperature change. And so it's about a degree if you work it out in Celsius. And what do we measure? That's if you look at the temperature change since 1900, it's about 1.3 degrees, and that's about the prediction. And
Oh,
so
interesting.
you say, well, now you say to yourself, that's interesting, because the important thing is, and I've talked about this in a variety of contexts, it's really important to understand that correlation is not causation. That correlating carbon dioxide change to a temperature change doesn't prove that carbon dioxide is in some sense causing it. But if you have an underlying physical mechanism that makes a prediction and you measure that correlation, then it gives you great confidence. Now you could say maybe there's some unknown science that we don't know that somehow cancels out all the basic fundamental stuff we expect and reproduces exactly what you would have predicted otherwise. A conspiracy, but no one knows of such a conspiracy. And if it walks like a duck and quacks like a duck, it's probably a duck.
Your
Go
book
ahead.
had tremendous information about the sun. One that struck me in particular was that every single day it's raining down thousands of times of energy that we need to actually power our existence.
Over
So we're
10,000 times. Yeah, with more than 10,000 times the total energy used by humanity each day comes down from the sun. So that's one of the reasons why you might think using the sun as a source of power would be a good thing.
Yeah.
So my question is actually how much solar energy is actually reaching the Earth? How much is being radiated back? And then how much are we actually capturing?
Well, what do you mean capturing? I mean,
like how much stays? How much stays? I know you were talking about
look, in equilibrium, if the Earth isn't heating up, then nothing stays. Namely, we're emitting as much as coming in. And that's what it was. Well, it is at any time, unless you make a sudden change in the system. But you can say that of the solar energy coming in, I think about 30% of it gets reflected already at the top of the atmosphere, and about 10% of it gets reflected by the Earth. The rest get absorbed by the atmosphere, and some of it makes it down to the Earth. And then, so you're talking basically about 50% of the, more or less, of the incident solar energy is the energy we're talking about that not only powers what's going on, but has to be ultimately radiated out if we're not going to heat up.
Right. Okay.
There's a figure in my book that shows all those numbers, and in any case, those are the rough numbers.
Yeah, and you had mentioned earlier that the greenhouse effect is a little bit of a misnomer. That's a phrase that my generation grew up with, our generations grew up with. I'm sure people would be interested in learning a little bit more about why that's not really an accurate description of what's going on.
Yeah, okay. And people at the time even recognized it. Unfortunately, kind of Fourier was the first person to use a greenhouse analogy, although he explained why it wasn't necessarily appropriate. A greenhouse, for those, greenhouses aren't so common anymore in cities, but cars are.
Yeah.
And if you're sitting in your car on a hot summer day, you know what happens. It gets damn hot. Mm-hmm. And the reason is and that's why you shouldn't put children in a car or animals in a car. And the reason is that the visible radiation coming in goes through your windows, gets absorbed, and gets re-radiated as infrared radiation. But the infrared radiation can't make it through the glass as effectively. So it gets stored. Now that's an important effect, and that is really at the heart of what the global greenhouse effect on the Earth. But what really is causing the heating up is the fact that also the air is trapped. You've got windows, that you've got glass that's stopping it from getting out. So the heat can't be moved by convection or as well, and the glass is kind of an insulator, so it can't move by conduction. And so, for example, if you open a window in your car, you will find it won't heat up, in spite of the fact that and so, well, it won't heat up as much. And so the Earth, people say, well, the Earth doesn't have windows. Okay, it's just open to space. So there's nothing that's stopping it. And the point is, the window part is the misnomer. The atmosphere is doing what the windows are doing. The atmosphere is absorbing the radiation and storing it, causing and radiating it back down to the Earth. And that's what's causing the heating up, or that's what's causing the Earth, in fact, to be warmer. We should all be very happy, because if it wasn't that case, as I say, the Earth would be 18 degrees below zero Celsius. Yeah. So I liken it. It's also perhaps an equally bad analogy in some ways, but maybe more clear, to a blanket. Because it's really important. What's really important to the greenhouse effect in the Earth, or what you call a greenhouse effect, is that the atmosphere is colder on the top than it is at the bottom. If it wasn't, if it was the same temperature everywhere, then it would be just like having the surface of the Earth. It's really important that it's colder and that it insulates. So the heat that's kept in the bottom doesn't make it all the way to the top. And so the way a blanket works, right, is your body is radiating heat, 100-watt heater at night. Okay, it's maybe 80 watts when you're sleeping. You have a blanket. You heat up underneath the blanket. But with the blanket is an insulator, so the bottom part of the blanket is heating up, but it's re-radiating that energy heat back to you.
Right.
The top part of the blanket is much colder, so it's not radiating your heat out into space, and that's exactly what the atmosphere is doing.
Wow, that's a great analogy and metaphor to help us visualize what's going on. So. Yeah, absolutely. It's interesting. Throughout your book, you were mentioning several different tipping points: Greenland, West Antarctica. I just want to put some stats out there and then have you talk about it because they were mind-boggling. The fact that you mentioned that there were giant icebergs, some 225 square miles, which is like 10 times the size of Manhattan, that are breaking off of glaciers. At one point, you also talked about the Larsen Ice Shelf, which that's a mass that's weighing 1 trillion tons, and
the size of a state. I think the size of the state of Delaware.
Yeah, exactly. The size of Delaware came off. So those are two examples, but what are some other tipping points that we should know about happening around the world?
Okay, now the important point about tipping points, I put them near the end of the book, is that I want to distinguish between the predictions that are pretty well written in stone, like the fact the Earth's temperature is going to increase by a few degrees, already has. The fact sea level is going to increase by up to a meter, more or less, no matter what we do this century. And that already has to be dealt with. Tipping points are much more complicated because they involve nonlinear effects, which are much harder to calculate. And therefore, they can be severe, but they're more uncertain. In one sense, they're uncertain about how to predict them, but they're not uncertain that they've happened. For example, the Greenland ice shelf is melting, okay? Now, the question is, will it disappear? And if it disappears, sea level will rise by 7 meters. 7 meters, 23 feet, okay? And then you're talking not just minimal stuff. You're talking about almost every coastal city in the world completely underwater.
Catastrophic, maybe.
And you might say, okay, yeah, but that's science fiction. And first of all, if it happens, we know at the rate, even if it happens, it's not going to happen it'll happen gradually over 1,000 years or 2,000 years, depending upon how hot we make the Earth. But even though it's science fiction in terms of being able to predict exactly what will cause that irrevocable melting, whether it collapses or whether we can save it, right? The point is it's melting now, but could we stop it? And right now you might say, yeah, if we do something, we can slow that down and stop it. But at some point, nonlinear effects could cause that to happen. And I'll explain those nonlinear effects in a second. But as speculative as that is, we know it happened. That's the point, is we know these things have happened. We can see the Greenland ice sheet melting, 15,000 years ago, and sea levels rising in the course of less than 1,000 years by almost 20 meters because there were other things happening. So we know these things have happened. It's not as if they haven't happened in the Earth before. So it's not science fiction in that sense. But so here's like an idea of the nonlinear effect. So let's take Greenland melting. First of all, the Arctic melting, as the sea ice melts, it doesn't change the water level. But what it does is it changes the albedo of the Earth. Water's darker than ice. Ice reflects light. So when the ice is gone, you're absorbing more radiation. What does that do? It heats up the water more. So that's a kind of nonlinear effect. Now, with the Greenland ice sheet, it's kind of interesting. There are a bunch of factors. One is that, the simplest one is as the sheet melts, it's a mile high, at least, in the Greenland ice sheet, and higher in some places. So the ice melts. What happens? The top of the ice sheet lowers in elevation. What happens when you go lower in elevation? It's warmer.
Right.
So then you've got, then it starts heating faster and et cetera, et cetera. And so that's one effect. But another effect that's kind of interesting is you also have warmer water around it, which is eating at the glaciers, which is causing the ice to go into the water, right, at the edges. So
Right.
warmer water melts the edge of the glacier, causes increased flow of ice into the sea, and that does raise sea level if it's ice that was on land.
Mm.
But there's another effect which is interesting, which is because it also, you might think that melting would produce precipitation, which should cause snow to fall. But
Right.
what's been discovered in a number of years in Greenland is that, in fact, it produces a local high pressure region, which causes it to be sunnier, which means less snow falls. And so,
Wow.
every year the snow is replenishing the ice sheet. And so that's another effect. Okay. And so that's how you can imagine a set of nonlinear effects eventually saying, okay, the tipping point, no matter what you do now, it's too late. All of these effects come together and it's irrevocable. It's no matter more or less what you do, it's gonna melt. But there are lots of but the thing is that effect there are nonlinear effects where one tipping point can affect another tipping point, where the melting of ice in the Arctic is changing both the temperature and salinity of the water, changing ocean currents. And in fact, as was in the news a lot just in the last few weeks, a major Atlantic current, AMOC, it's called Atlantic Meridional Ocean Current, or something like that. I forget what AMOC stands for, but it includes the Gulf Stream, and it's weakening.
Oh, wow.
That Gulf Stream takes warm water up off the coast of the east coast of the United States, goes to Europe, and is responsible for the fact that Europe, even though it's at a much higher latitude than most of the United States, is warmer. It's warmer than Canada. Okay.
Oh, yeah, fascinating.
And the reason, if you surprise yourself sometime and look and ask where Spain is compared to, Spain, which is nice, the south coast part of Spain, which is nice and warm. Look at it. It's like the northern part of the United States. It's warmer in part because of the moderation of that ocean current. And if that's weakening, you expect Europe to become colder. But also it affects the precipitation, not just in Europe, but as that ocean stream goes down to the south, precipitation in Central Africa, where it could cause reduction in precipitation and famines, reduction in precipitation in South America, which could turn rainforests into savannas, which may not seem like a big deal, except when the rainforest disappears, it donates a lot of carbon to the atmosphere, right? Because of all those trees. So you see there can be all of it. And then, of course, there's one of the biggest tipping points, or one of the bigger tipping points, is the incredible storage of methane in permafrost in Siberia, which could be released en masse again. And methane is a huge greenhouse gas. So that's the kind of thing that once again could happen as a trigger event and not be gradual like sea level rise or temperature rise, but be sudden. So there are a lot of things that are possible. And then what I like to say is that I'm reminded of Clint Eastwood in Dirty Harry movies, when he used to say, "You feeling lucky, punk?" And the question is, well, maybe they're just possible. So maybe we can feel lucky. And you got to ask yourself the question: how much are you willing to risk, versus how much are you not willing to risk? And if you can avoid some of that risk by doing something that isn't even painful, like maybe exploiting new innovation of new technologies that can help economies or helping the world in other places, then is it worth it? And the curve, the graph that really caused my thinking to change the first time, and I forget whether it was Jim Hansen or a friend of mine who was also the chair of the director of the Scripps Institute of Oceanography at the time, was seeing that there's an amazing correlation over 400,000 years between carbon dioxide levels and temperature. It's just amazing, telling you that the theory generally works. Okay, but and the fit between the two is remarkable. Again, correlation isn't causation, but the theory you can predict what the temperature would have been, and it's more or less the same as what is observed to be. But overlaid on that, you can then look at sea levels and look at Red Sea data over that time, and you see the same correlation. And sea levels change by not 1 meter, not 7 meters, but 120 meters over the course of the last 400,000 years. In fact, over the last 30,000 years. And that is a large number, right?
Yeah.
That's 300 feet.
Yeah.
And so, I mean, in this case, they largely went down, but they sometimes were higher than the current levels. But sea levels can change by that much. And that's what first hit me. When I saw that, I thought, okay, we really need to begin to think about this, because if sea levels naturally can change by this order of magnitude, and we're putting the Earth in a situation where it's never been before in terms of carbon,
Right.
we're not predicting 120 meters of sea level rise, but 10 or 20 meters of sea level rise over a millennium is certainly not unheard of in the history
Right.
of the Earth.
Yeah, absolutely. Yeah, I wanted to ask you, see if we can kind of address the skeptics head on, because I know that you're a famous skeptic, Dr. Krauss. I wanted to read a quote here. According to NASA, there are multiple studies published in peer-reviewed scientific journals that show that 97% or more of actively publishing climate scientists agree climate warming trends over the past century are extremely likely due to human activities. Some 3%, however, are not of this opinion. So I wanted to ask you, have you ever encountered any argument from these dissenters, those scientists that are breaking with consensus that is worth steel manning? Is there any interesting arguments coming from that side of the
Well,
faction at all?
let's first say I hate that statistic. Okay, I hate the use of that statistic. Science is not done by democracy. We don't all vote say, okay, we all think gravity makes you fall. Oh, you don't think gravity makes you fall? Okay. Oh, maybe 40% of you don't think? Well, then gravity doesn't make you fall. Okay. I mean, it's not done that way. Okay. And you make predictions, you test them, and the theories that work, and the ones that don't get thrown out. So whether there's 97% or not, first of all, let me point out, I just had to talk to journalists. There was a conference of 2,000 people, I think it was, who thought the Earth was flat, most of them PhDs, okay? So the fact that those PhDs think the Earth is flat, all it means to get a PhD is you got a PhD. It doesn't mean a damn thing, right? So therefore, taking percentages of people and saying, look, there's some PhD scientists that think the Earth is flat. Therefore, maybe there's a possibility it's flat. Well, it's not flat. You want to know? Go around it. I've done it. Okay. And I don't care whether there's 1% or 0.5%. It doesn't matter. They're wrong, because the great thing about science is one side is just wrong usually. Okay.
Yeah.
And there are things that are controversial, and we learn, and that's okay. But so what they're saying is that with 97%, that it's not controversial among climate scientists. But the major thing is that the predictions, as I said to you, you can use the theory predicts, and you see what the theory predicts, and on the whole, it's right. Okay. Now, there are some people there are skeptics and there are deniers, and I think there's a difference between the two, and you should really be careful about using that term for everyone. There are those who say, look, it's not happening. It doesn't matter. It's not happening. They're the same kind of people who say the Earth is 6,000 years old. I don't care what you say. It's not happening. Or the Earth is flat. I don't care what you say. It's not happening. There are skeptics, however, that's quite a different thing, to say, well, first let's look at the weak points of these arguments. And some of those people, for example, the impact of clouds or precipitation, and so they would point out, hey, the models don't necessarily address clouds very well. And so that's a true point initially. But what's happened is the models have gotten better and have addressed clouds, and the results still remain the same. And the basic underlying physics is independent in some sense of how effectively clouds do things, because we're talking about energy in and energy out. The details of temperature change here or there, ice melting here or there, depend on complex models. Okay, and so that those are details are subject to sometimes more uncertainty, because more variables need to take into account. But the net effects, the global effects, which are the things I really want to concentrate on. It's what I even do in my physics study. Looking at the whole scale of the universe is sometimes easier than understanding what's happening on Earth. But anyway, so some of those people who don't agree might say, I don't accept the predictions of those models as much as other people. Okay. And then sometimes, the problem is with scientists, it's like looking at children, who are always beautiful to their parents.
Yeah.
And so people who spend their life working on, say, a cloud model, and their model, they're often less willing to accept other people's models, and that so there's a lot of that in science, especially at the edge of it. And so you expect some people to say, well, I just don't trust it. I know I debated one scientist once who was a skeptic / denier, and a good friend of mine who was also there and is a client scientist was pointing out that basically, and I'm not going to name the name, but basically he felt he was smarter and he was very smart. Okay, he's at a major institution. That he was smarter than the people doing the models. He hadn't done them. He hadn't followed them. But he basically said, if I'm not doing them, they can't be very good. And there's so it's a human kind of thing too. And my friend Freeman Dyson, who was was an amazingly smart scientist. Well, he was naive, and he was saying, well, and he didn't doubt, by the way, the existence of global warming. What he said was maybe it'll be good for the Earth, but his arguments, he didn't follow the models in detail either. And he was smarter than most of the others, but if he didn't do the work, and so his claims were, I would say, in that sense, irresponsible. I've had many conversations with him before he died about it.
Lawrence, let's get back to your book. Actually,
3% doesn't mean much. You're going to have.
I appreciate that answer. Yeah, absolutely.
As I say, there are probably some percentage of scientists who think gravity makes you fall up. I don't know them, but I wouldn't be surprised they're somewhere. Anyway.
Now let's get back to your book, because it is actually one of those books where you're not addressing the politics. Like, you make it very clear that these are facts, and you make it very clear for someone like me who's reading it, like, hey, if you read this book, you can address your own questions, you can make your own claims, you can make your own decisions. So I want to actually focus on your book, because one interesting part of it was how you talk about how oceans play a huge role in climate on Earth. And I want to read a stat that broke my brain. Okay. To get an idea, quote, to get an idea of the heat capacity of the world's oceans compared to the heat dumped in the oceans by humanity so far, consider the measured rise in ocean temperature in 2019 of 0.075 degrees Celsius compared to the 1981 to 2020 average temperature. Just that measured difference corresponds to the additional heat that would have been produced by setting off 3.6 billion Hiroshima atom bomb explosions in the ocean, or about 5 Hiroshima bombs of heat every second, day and night, 365 days a year for the past 25 years. To me, that was one of the most fascinating facts in the book. It led to the whole idea that you were trying to present around thermal expansion and how oceans play a huge role in the climate on Earth. So can you expand on that for us?
Well, it's a remarkable number. Things like that are remarkable because they confront your own misconceptions, and that's how people learn. That's what people remember. That's why, examples like that are really important. But the point is that the point of this is that the Earth is largely an ocean planet. The oceans are deep, and circulation takes a while. It takes a long time for heat to thermalize. So, for example, even if we stop, keep the carbon level where it is, and keep the Earth's temperature where it is, the atmospheric temperature where it is, the ocean temperature will continue to rise, and it will continue to expand. So that's what I mean by the fact that you're more or less guaranteed to have at least a quarter of a meter of sea level rise just by thermal expansion
alone.
And the fact that but it does demonstrate how much heat we're talking about. That 0.075 does not seem like a great deal of temperature, but there's a lot of ocean. And so I think that example is a really good example because it shows that ultimately, more or less, the oceans are going to determine not only the carbon dioxide level, but the temperature level, and the impact of temperature on the Earth, because they're the ones that are storing the heat. The atmosphere stores very little heat compared to the ocean. It takes a long time for the ocean, therefore, to build up its temperature, because it takes a lot of heat to produce a given temperature change if there's a lot of water. But it also means that it's going to take a long time for that heat to dissipate, if you wish. Okay, and so, but it also means that what happens on Earth will be governed by the oceans. For example, as one of the graphs in my book shows, the northern hemisphere, if you look at predictions in the near term, the northern oceans are going to increase in temperature much more than the southern ocean because it's not as deep. Okay, and that means you'll see temperature, the air temperature as well, is going to be hotter more quickly in the north than the south. But over the course of 1,000 years, eventually the south is going to be much hotter than the north. Not much hotter, but the increase in temperature will be greater. The north will have begun. If you turn off carbon production, the north will have already begun to cool down in 500 or 1,000 years, whereas the south will have the end result will have heated up.
Wow.
And so the circulation in the ocean, the abundance of the ocean is going to determine over time which parts of the earth heat up quickest, which cool down quickest. Okay.
So I'm wondering if people should be working on technology. Like, what would you say in terms of a strong call to action? I know we have a couple minutes here left. What would you say is a strong call to action for the people listening? Like, what technology can they think about creating? What do you think that they should be trying to accomplish?
Well, look, the problem isn't technological on the most part; it's political. Okay, let me say that. I have great optimism. I was going to say faith, but I don't like that word. I have great optimism about our ability to do technology and to address and mediate a number of these problems. It's why I think it's irresponsible to say the world is going to, as some people on the left have done, say that if we don't do anything now, in 20 years, our children will be dead. I just don't think that's fair to say. We can do a lot. And of course, there are technologies, solar technology. There are they're not carbon free because it costs money to produce them, and it costs energy to produce them and carbon in production of them. But but there are more or less carbon neutral production technologies like solar power, which are becoming cheaper, more efficient, etc. So obviously, those things are going to be used just because people are going to vote with their dollar, with their pocketbooks. As solar energy becomes cheaper than coal energy, it'll be more used. Of course, the problem is then one of battery technology, because the sun is shining only half the day. Not here in Oregon, it's not always much of the day at all. And so you have to figure out ways to store that energy, and that's currently an issue. And improving battery technology is a real area where technological innovation is required. But there are other ways, of course, that are important, and one is conservation. One is just simply not using as much energy, and that's been true for 30 years. And I remember someone I know named Avery Lovins has been pointing out that it's a lot cheaper to save. At the time he pointed out, and I hope it's changed, that in skyscrapers, 50% of the air conditioning load, at least, maybe more, was used to just take away the excess heat produced by lighting.
Wow.
And so if you did it more simply, you could avoid that. So those kind of being smarter in design of buildings is important. But a lot of carbon is produced by transportation and some of it by agriculture. So we can look at those things. We can also look at energy technologies that exist that don't produce carbon, and one of them is nuclear power, which had a bad rap, but really, in terms of the number of people who've ever died, it's small compared to coal power. And so, although people are afraid of the word radioactivity, the nuclear power definitely should be part of the equation. And it's unfortunate in parts of the states that people are trying to close down nuclear power plants when in fact they shouldn't be.
Right.
Okay, because of things that have happened in the past, from Three Mile to Fukushima to Chernobyl.
Yeah.
Mm-hmm.
But you can ask how many people still. It's debatable. I think it's still, even if you take the worst figures for how many people may have died as a result of Chernobyl, and some people would argue it's very few at all. But if you take the worst figures, it's still small, I think, compared to the number of people who died due to coal burning, due to pollution of coal burning. So you want to, there's no silver bullet. You want to do a lot of different things, each of which can help contribute to making us a carbon neutral world. And I think we should be doing all of those. Mm-hmm. At the same time, as I say, I think what we need to also look is an infrastructure to helping the third world deal with the effects of climate change, and also come up. They want to be energy users as much as we are, because that energy correlates to wealth in some sense in the world, and they have every right to do that. And so we need to help them do that in an efficient way. So it's a lot of little things, and what we can, and if you feel daunted as a human being, well, you can look at your own carbon footprint. Yeah, you can look at how to reduce it. One of the ways I would argue is to have fewer children, but probably reducing your own footprint is one thing. But if that feels hopeless to you, one thing you can do is educate yourself about the issues. And we all have soapboxes. Because governments, as I've often said, and I've said 1,000 times in the last few weeks, they don't lead, they follow. And that means, if the public is motivated, governments are going to follow regardless, whether they're a dictatorship or democracy. And the one bit of hope I may have, if I have hope on the good days, is that generationally, young people seem to accept that human-induced climate change is real.
Mm-hmm.
Right.
And that gives me hope in the sense that gay marriage gave me hope. That 20 years ago I would have thought I'd never see that gay marriage wouldn't be legal.
Yeah.
But because people, my daughter's generation, that knew gay people, it was no big deal for them. I knew it didn't matter what older senators or Supreme Court justices did. It was done. And as I said to you earlier, physics proceeds one funeral at a time. The world proceeds many funerals at a time. And if young people are view this as a big issue, then you can be reasonably assured, one would hope, that's going to mean in a generation there can be activity. And we're already seeing it in some sense, with the shift from the last administration of the United States to the current administration. You're already seeing a shift. But once again, I worry, even in the current administration, about people who have a religious belief in climate change versus a empirical belief. The religious belief starts talking about doomsday and apocalypse, and I think that is wrong because it turns people off. When you say, look, when you say that 100 million people are going to be dead in 10 years and it doesn't happen, what does it mean? Then the rest of the people become skeptical, the boy who cried wolf. And so we have to keep grounded in reality, and that's why I produced a book just on the science rather than the policy. There are lots of policies one can talk about, but we at least have to be straight on the science before we can have rational public policy. And that's and people can use this is written for the skeptics, but also for the people who want to have arguments, that they can, not arguments when they have literal arguments, but when they want to talk to their neighbors, their friends, their family, their congregation, their children,
Yeah, it creates a foundation for where that debate can start when you have the facts. And one thing I love about you is that you spent this past weekend, we're recording here on Monday, March 8th, and you spent this past weekend signing over 500 copies for each member of Congress just to get the fact out. So I appreciate
we're trying,
your work.
and it's not free. I run a nonprofit foundation, the Origins Project Foundation, which does run the Origins podcast, and did run a public lecture I gave on the subject recently. And so we're trying to raise money. It's a tax-free foundation to be able to do this. So there's the buying of the books. By the way, I'm foregoing my royalties in those in case people are wondering if this is some money making it free. And then there's the mailing, packaging, etc. And so we do have a GoFundMe, which is sort of a little more than half filled now, to try and do that. And we're going to do it one way or another in the next few weeks. I was just getting, in fact, my mailing labels for Congress today.
Nice.
And we're doing it because we hope that it'll have an impact. Yeah. Anyway,
that's wonderful.
Not lobbying. Once again, it's not lobbying for Democrat or Republican or for a specific policy. It's just saying, hey, here, maybe you or your staffers might learn something from this.
Exactly.
Right. Yeah. Well, we appreciate the words of hope and optimism, and we'll certainly be putting the GoFundMe in our show notes. So thank you for doing that.
Sure. Well, it's been a fun discussion. It's been not the end yet of a long day, but in the middle of a long day. And
absolutely.
I'm glad I had the energy to go through it with you. And
we appreciate it.
I appreciate your, but I also appreciate, I do a podcast. I do my homework, and I appreciate when people do their homework, and I'm glad you guys did too. So it's really great.
Awesome. So one last question, because we've been ending our episodes with one final question for our guests. Let me ask you this, Lawrence. What do you think is a modern masterpiece?
There are, I should say, when you say a modern masterpiece, you may ask me what is the most amazing modern masterpiece. And I tend not to think that way because the world amazes me every single day with masterpieces. So a modern masterpiece could be the Perseverance rover that landed on Mars remotely without human, and that was amazing to me.
Absolutely.
A modern masterpiece could be movies by my friends, by Werner Herzog, one of which I was in, which wasn't a masterpiece.
Oh, nice.
Other people don't think it was a masterpiece. It was fun for me.
Subjective.
Or great films, human science is part of our culture, and we amaze me every day by that's what makes it so sad in some sense. The heights that humanity can rise to with great music, with great literature, great art, or great science amaze me. And they're all examples of the human imagination and the human ability. So humanity in some ways is a masterpiece, but it's also a tragedy. And
Beautiful.
The subject of history is in some sense matching that masterpiece with the tragedy and where it goes from here.
That's amazing. Thank you for sharing space with us, and we appreciate it.
Sure, thank you. Okay, you take care.
If you enjoyed this episode, you can sign up for the Rising Weekly newsletter sent out each week.
Every Friday, we expand on the episode with insights, recommendations, and more.
You can sign up at risinglatterly.com.
Thank you.